Welcome students to the second lecture for Module 6 on simple linear regression. Regression allows us to predict for individuals and is closely related to correlation. Because regression is closely related to correlational tests, the reasons for doing a regression are very similar. So in other words, if you remember with our Z, T, and F tests, we lose variability. We lose variability for the individuals. And so it's the same thing for regression. We want to retain individual differences in our analyses. We know that people differ, and how they differ best represents the overall population, and so we want to retain that variability. And we can't do that with Z, T, or F, but we can do that with correlation, and we can do that with regression. In addition to the fact that we lose variability with our Z, T, and F tests, we also can't predict for individuals. And again, that's because with our Z, T, and F tests, we're using groups and the averages of groups to do our analyses, and we're not using individuals. So we can't predict for individuals. We can predict for groups, but not for individuals with those tests. Additionally, our F tests are limited to 3 independent variables. So if you remember with our F tests, once we get beyond 3 independent variables, it's very difficult for us cognitively to understand our analysis. We're 3-dimensional beings. We see in 3 dimensions. We understand in 3 dimensions. And so if each independent variable is a dimension, it's very difficult for us to understand more than 3 independent variables because that's more than what we can cognitively handle with the dimensions we're used to. So in that sense, regression allows us to retain all 3 of those limitations of Z, T, and F tests. We retain individual variability, and because of that we're able to predict for individuals, and then also with a regression we can have more than 3 independent variables. In fact, we can have as many independent variables as we like, as long as they're uncorrelated with each other. And so regression itself is an extension of correlation. So once we have a correlation coefficient between our variables, we can then move forward, do a few more calculations, and do a regression analysis. Now you may remember that when we get a correlation coefficient, that we're looking at the relationship between 2 variables. And we know that those 2 variables are not causally related, and so we don't really have a true independent variable. We can't say one variable causes the other because we don't have random assignment to conditions. We can just state that they're related, and we know that there's no causal relationship between them. But with regression, we're saying that one variable predicts another variable. So in other words, we're saying that one variable in essence is causing, although it's not a causal relationship, it's causing or influencing another variable. And so we have to choose one of our variables from our correlation to be the independent variable. And so we call this variable the predictor variable. And so independent variable and predictor variable are synonymous with each other. They mean the same thing. It's the variable that we are manipulating in some way. So with regression, we choose one of our variables, and it doesn't really matter which one we choose because it's based on correlation where there's no causal relationship, but the one we choose we'll call the independent or the predictor variable. And so again, we can have as many of these predictor variables as we like, as long as they're uncorrelated with each other. When we say that, we mean that they are orthogonal to each other. So the word orthogonal means that they are uncorrelated with each other. They're unrelated. So we can have as many predictor variables as we like, as long as they're unrelated to each other, or what we call orthogonal. And when we do this, if we have more than 2 predictor variables, so 2 or more, then we'll call that a multiple regression, something that we'll talk about in class later on. So regression, we can have as many predictor variables as we like. If we have more than one, we call that multiple regression, and that sets us up for our regression analysis. If one of the variables that we pick is the predictor variable or the independent variable, then that means the remaining variable must be the dependent variable. And so the dependent variable is what we call the criterion variable. Sometimes it's called the outcome variable. And so the criterion variable or the outcome variable is the variable that we're trying to predict. And so if I wanted to predict grades from the number of absences, then grades would be my criterion or the dependent variable. And I'm going to try to predict grades, our dependent variable, our criterion variable, from number of absences. So absences would be the predictor. So the number of absences a student has, I should be able to predict within a realm of confidence the grade for any particular student. So let's use that example of grades and absences for individual students that we use for correlation, and let's talk about it in terms of a regression. So again, regression are additional analyses after you do your correlation. And so we talked about before that there is a negative relationship between absences and course grades, that as absences increase, there tends to be a decrease in the grades for students. And that relationship as a correlation coefficient is r equals negative 0.58. And that's a significant relationship between the two. So you've seen this scatter plot before. Now what is new in this scatter plot here is that if we look at just course grade by itself, so again this is without absences, this is only looking at course grade, we see that the past 517 students have an average grade in the course at the end of the semester of an 81.8%. So if we don't look at absences, we only look at course grade, and we find the averages of all 517 students for their final grade in the course, we end up with an average of 81.8%. And so that's the average for course grade, or the variable on the y-axis. So you'll see in the equation of the line you have y hat, and so that little arrow above the y is called a hat, or it's a caret. So we call y hat equals 81.8%. What that means is that our best guess for any student's grade in the course at the end of a semester is 81.8% if we know nothing else about that particular student. So if we don't know about any other variables that may matter to course grade, our best guess for any one student who finishes this course is a grade of 81.8%. Now, of course, as you can tell from the scatter plot, not everyone is scoring exactly an 81.8%. That there's a lot of variability, there's a lot of individual differences. So if each point on this scatter plot is a student in the course, you'll see that their grade will deviate from that average of 81.8%. And so we call that error. So our best guess is a grade of 81.8%. and how far off any one particular student is from that particular estimate of 81.8%, we will call error. So essentially it's the actual grade minus our predicted grade of 81.8%. And so for some of the students, that error is very small. In other words, their actual grade is very close to the average of course grade of all students in the class. However, for some other students, that error is much larger. In other words, their actual score is much different than our predicted score of 81.8%. And so our goal with regression is to minimize the error or reduce the error in our predictions. And one way we can do that is by adding predictors. And so in this case, we may add a predictor of absences. So if we can add a predictor and get a better estimate with less error, then we can do a better job of predicting students' grades at the end of the semester. If we add a predictor such as absences, then we can create a new line that best represents course grades at the end of the semester, given the number of absences students have. And that's what this blue dashed line represents, is our new line of best fit once we include absences as a predictor. And so you'll notice for those 2 points that we just talked about that the error has decreased because of this predictor. So if we add absences into our equation, we can reduce the error from any one individual student in the course when predicting their course grade. And so instead of just estimating what a student's grade at the end of the course will be by just looking at the average of course grades, we can also take into fact that students have absences. And if we account for those absences, we can get a better prediction of course grade. And so our new equation now, once we add a predictor, will be y hat, so again y with the arrow or the caret above it, will equal 90.12 minus 1.33 times x, where x is the number of absences. So we can get a predicted grade by taking a constant of 90.12% minus 1.33% times the number of absences. And that will give us a better prediction. Now you'll note here that there are still errors in our model, that there are still discrepancies between actual scores and predicted scores, but that error has now been reduced. And so we have a better prediction if we include absences. let's take a closer look at the regression equation or the prediction equation. So here's the equation by itself, so without any numbers. And so our equation is y hat, or the outcome or criterion that we're trying to predict, equals a plus b times x. Now you'll note that this equation is the same equation for a line that you've learned a long time ago in grade school. And so the idea is very similar, except we'll account for error in our prediction equation. Alright, so y hat in this case is our predicted criterion. That would be a student's individual grades at the end of the semester. A would equal our y-axis intercept when x equals 0. So in other words, when there are no absences, what would we predict a student's grade to be? In this case, we would predict it to be a 90.12% based on all the data points from previous semesters. Alright, so then B is the slope of the regression line, or the slope of the line. It's the rise over the run. So in other words, it's the increase or decrease in the percent for grades given every absence. So in this case, based on our data, we have a negative relationship, so we expect grades to decrease for every absence. In this case, we would expect that grades will decrease by 1.33% for every absence a student has on average. And then x is our predictor variable. In this case, it's the number of absences. So we can take the number of absences a student has, multiply it by the percent decrease we would expect, in this case 1.33%, and then add that value to our y-axis intercept when we expect there to be no absences, in this case 90.12%. So we end up with a prediction equation that is y hat equals 90.12% plus a negative 1.33% times the number of absences. So we can plot that line on our scatter plot. You'll notice that when x equals 0, that on the y-axis course grade is about a 90%. If we want to be very specific, we'd say 90.12. And that you'll notice for every increase in absences, the line decreases by 1.33% of the course grade. And so you'll note that even though we have a better prediction here, that there's still some error from each of the points to that regression line or our prediction line. That means that for any particular prediction for a single student, that there is a probability that we are going to be off a little bit. In other words, our prediction is not going to be exact, that there is a range of where our prediction value could fall. And that's what we call the standard error of the estimate. So the standard error of the estimate gives us an estimate of how much error is in our prediction. Now if we want to get a particular number for the standard error of the estimate, then we'd have to take the square root of the mean squared within, or in other words, the square root of the error variance. So if you remember from ANOVA, MS within is error variance in the model. And we'll talk about that in class, and I'll show you how to get the mean squared within so that we can get an estimate of the standard error. If we wanted to put the standard error of the estimate into words, we can say that the standard error of the estimate is the number of percentage points in course grade that on average we could be off for any single prediction. So if we had a student who had a certain number of absences, we could get a prediction, but that prediction is likely to be off by a certain amount. And so we can create a range of where we would expect that particular student's grade to fall. So now we have a prediction range rather than just a prediction value. And that's what the standard error of the estimate gives us. In addition to our prediction equation, we can now add the standard error of the estimate. In this case, for our given data, our standard error of the estimate is 7.68%. So that means that for any particular student that we give an estimate for their course grade, that we could be off by 7.68%. And so that means that once I complete my regression, I have a prediction equation such as y hat, or the course grade, equals 90.12 minus 1.33 times x, when there's an estimate of error of 7.68%. And so that's simple linear regression. Now before we end the lecture, let's talk about, just briefly and conceptually, let's talk about multiple regression. If you remember back towards the beginning of the lecture, we talked about that with regression, we're not limited to the number of predictor variables, that we can have as many as we like as long as they're uncorrelated with each other. And so if we have more than one predictor variable or more than one independent variable, then we have what's called multiple regression. So we have multiple predictors for our outcome. So in this case, we might add another predictor to estimating a student's course grade. Now, the more predictors we have, the better our estimate's going to be. In other words, the standard error of the estimate will decrease. That the percent that we could be wrong will get smaller for the more predictors that we have. When we add another predictor, our prediction equation changes just slightly. And so if you notice here, we still have a plus b times x, but now we're going to add another coefficient or another b value, another slope, and another x value, and we'll call that b2 and x2. And so let's say that instead of just looking at absences, we also want to look at the number of hours students study when it comes to predicting their grade in a course. And so now we add a second predictor. That predictor is hours studied, and so we can get an estimate of how many hours a student studies a week and plug that into our equation. And that should give us a better estimate of a student's course grade that has less error. And so our new equation would now be y hat, which is our criterion, in this case the course grade of a student at the end of the semester, equals a, which is a constant that represents the y-axis intercept when both x1 and x2 equal 0. So in other words, when students have 0 absences and they don't study at all during the week, we can get an estimate of a student's grade. And so that's a, the y-intercept. We then have the slope for the first predictor variable, which is number of absences. We also have the slope for the second predictor variable, which is b2. That will be the slope for hours studied. And then we'll have our values for x1 and x2 that we would plug into our equation that represents any one student's number of absences and their number of hours studied. And so for multiple regression, I'm not asking you to come up with the b values or the slopes in this case, or even the constant. We won't do that because that's beyond the scope of this course. But you should know conceptually what multiple regression is, that we have multiple predictor variables, and that for any one of those predictor variables we have a slope that corresponds with it for our equation. Now ultimately, when we're done in class, you should be able to use the equation, although you won't generate all the numbers for the equation, and we'll talk about that in class. Alright, that concludes our lecture for today. I hope you have a great rest of the day, and I'll see you in class. Thank you.